Welcome to this session. Till now we discussed about different basics of our electromagnetic theory. So what are electrostatics, what are magnetostatics, and what are different applications of electrostatics and magnetostatics. Later we discussed about time varying fields, and then how the electromagnetic wave will be transmitted through different media like wave propagation, that is in free space, or different dielectric medium or conducting medium. And later we discussed about transmission lines. So how the wave propagation will be taking place in transmission lines, how the signal will be transmitted, how the transmission lines will be analyzed. And later we discussed about the waveguides. So they are meant for the high frequency applications. At high frequencies, how the waveguide will be useful for transmission of electromagnetic wave, and what are different characteristics of waveguides, and some problems on our discussed applications. Now we are going to observe the applications of electromagnetic waves, where the electromagnetic wave will be applied. The electromagnetic waves, EM waves, will be applied purely in communications. The major application is in communications. So for free space communication nowadays, these are widely used. So without this electromagnetic wave, there is no free space communication, or in simple word, there is no communication at all nowadays. So for such free space communication, what are the major tools we require? For any communication, we require a transmitter, a receiver, and in between transmitter and receiver, some intermediate circuitry will be there. That circuitry will modulate the signal or encode the signal, or somewhat it changes the signal form, and that changed signal will transmit it through a channel. Here for free space communication, the name itself indicating that the communication is through free space. For free space communication, we require another device which can convert the signal which is generated by the transmitter to electromagnetic wave. Or at the reception end, or at the receiving end, we require a device which can take the electromagnetic wave, and that must be converted to the voltage and current form. So here clearly we are concentrating on such application, that a device which can convert the intermediate signal which is modulated or somewhat changed, which is in the form of electric signal, that is the voltage and current signal, to electromagnetic wave, or the electromagnetic wave to voltage and current. Such device is called as antenna. Now we will discuss about the basics of antenna, what are different parameters which are related to the antenna, and how the antenna will be analyzed, we will discuss in this session. So initially we will start with the definition of an antenna. What is an antenna? As we know, as I said, the antenna is a device which can convert the basic electrical signal into the electromagnetic wave, or the electromagnetic wave into electrical signal. This is applicable in both cases. An antenna can convert electrical signal which is in the form of voltage and current to electromagnetic wave, that is in the terms of E and H. The fields will exist after emerging from the antenna. Similarly, it can receive the electromagnetic wave, that is which is in the form of E and H, and that will be converted to the voltage and current. So the antenna definition can be taken like this: a means of radiating or receiving a radio waves. So it can radiate the radio waves or receive the radio waves, or an interface between a circuit and free space. As I said, till the antenna we have a circuit. That circuit can generate an audio signal, that circuit can generate a video signal, that circuit can generate an image. All these things will be just electrical signals which is in the form of voltage and current. Now that particular voltage and current will be converted to E and H. So simply this can be taken as an interface between the circuitry that what we have and the free space, or a transducer which converts the time varying currents to the photons. How the electromagnetic wave will be transmitted? It's in form of photons. That's energy packets will be transmitted. How the energy packets will be observed obtained? That's using our antenna. So this is a simple definition of antenna. Now with this one we will start different categories of antennas. What are different types of antennas, and what are different parameters of our antennas? Now we will observe how radiation will exist for the help of an antenna. Just you observe this figure. If you are observing this figure, in this figure you have a structure which is flared out at one end. So clearly if you are observing, this is a conductor. It was not written here, but remember that this is a structure which is made up of a conductor, and at one end of the conductor the signal was connected. This is the signal what we are connecting, and at another end it is simply flared out. Now with this structure, how you will get radiation? Just observe, whenever we are connecting a voltage source or the current source here, obviously some charges will be generated and those charges will give you different polarities to the conducting structure. At this particular location we have a positively charged one, and at this location we have a negatively charged one. With this one, a little electric field and magnetic field will be generated within the structure itself, and those electric field and magnetic field or the different poles will transmitted up to this end. Now at this end it was completely flared out or the simple opened out structure. Whenever it is opened out structure, even though if it is opened out, that's simply the electric field or the magnetic field will comes into the end, and at this one, that what we have is a free space. Because of we have a free space here, that there is no particular location or there is no particular space to transmit from this conductor to the another medium. There is no medium here. The medium is nothing but the free space. So here what it does is just it detaches from the conducting medium and goes to the space as an electromagnetic wave. And clearly remember that up to this particular point, this is the voltage and current signal that what we are considering for analysis as well as existing purpose. And after this one, after this particular point x naught, this will comes into the electromagnetic wave will comes into the picture, and this will be goes out to the free space like just a balloon, a simple smoke that what you can imagine, like a smoke, just it will goes to the free space. This is a simple radiation mechanism from an antenna. Now we will observe different classification of antennas. That's how the antennas will be classified. Nowadays we are observing different antennas for different applications. If you take TV reception, on every home you are observing a simple antenna. There is a parabolic reflector or a hyperbolic reflector. That is also called as the dish antenna. In the olden days, for the TV reception, we used to have an array that is called as Aggie-Woda array, Aggie antenna. In the mobile phone application, we may have a simple patch antenna, or for some of the applications you may have a spiral antenna. For optical communications or some other satellite communication applications, you may have a spiral antenna or a helical antenna. Like that, for different applications, different antennas will be there. Now just I will go what are different classification of antennas. Now observe, the antennas were classified based on different parameters. Like the first one is based on shape, how aperture is observed, how the aperture is given. That if the aperture is like a parabola, then it is said to be a parabolic reflector. If the aperture is like a horn, then it is said to be a horn antenna. If it is a simple thin linear wire, a linear wire antenna or dipole antenna, like that, purely depend upon the shape, the antennas were classified. Now observe the second category. The second one based on polarization. So based on polarization, already we discussed about different polarizations. So what are the polarizations we have? Linear polarization, circular polarization, elliptical polarization. Like that, we have different polarizations. For different applications, different antennas will be there. For linearly polarized signal, we are supposed to use some of the antennas like a linear wire antenna. For elliptically polarized or circularly polarized, for circularly polarized antenna, we are supposed to use our helical structure, a helical antenna. Or for elliptically polarized, an array will be used, a patch antenna array will be used with different inputs. Like that, depend upon the polarization type what we require, the antennas will be classified. And go to the third category. So based on operating frequency. So based on operating frequency, the antennas can be made for VHF, that's a very high frequency applications, ultra high frequency applications, or super high frequency applications, medium frequency applications. Like that, depend upon the application, that the frequency is divided for into different categories for different applications. A radio wave will use some of the frequencies. Satellite communication, for the satellite communication, the frequencies are different. For microwave communication, the frequencies are little bit different. So based on the frequency bands, the antennas were classified and they will be manufactured with their wavelength, or the dimension is incomparable with the wavelength of that particular frequency. And come to the next one, based on applications. The fourth category is based on application. So as I said, different applications are there. To receive a TV signal, we require one type of antenna. To receive a radio signal, we require another type of antenna. To receive a cell phone signal, we require one type of antenna. And for radar application, one type of antenna will be there. Like that, different antennas will be classified and manufactured, so purely depend upon their applications. The last one is based on complexity. Complexity means that's how much gain we require. and here complexity is nothing but the number of elements we are using that particular antenna structure. A basic antenna will be there called as a Hertzian dipole. So that is the basic antenna, and which will be useful for manufacturing of different complex antennas. That those complex arrays will be used for analysis of our space or the generation of signal with high directivity, high gain. Like that, depend upon the application also. Here also the application will comes into the picture. Depend upon the application also, the complexity will be decided. These are few categories of our antennas that the classification is depend upon some of the parameters. Next, just observe what are different types of antennas. Here I gave a simple chart to observe what are different types of antennas depend upon different parameters. Now observe what are different antennas we have. Here the antennas are classified as end fires. End fire is nothing but an array. End fire array will gives you the radiation pattern in parallel with the axis of our array. So this is end fire array, and under end fire array different antennas are there, that is polyrods, helices, Aggie-Oda. This Aggie-Oda is very much known to us, that is which is an antenna which will be useful for reception of our TV in our olden days. And a log periodic antenna, conical spirals, all these antennas, the antennas that what I am showing under end fire will generate the radiation pattern in parallel with the axis of our antenna array. Next, the loop antennas. As a loop antennas also will be useful for transmission and reception of the signal, especially for elliptical or circularly polarized signals. And the next one is for dipoles. So under dipole name itself indicating that the two poles will be there. Under dipole we have folded dipole. So this folded dipole is the major element in our Aggie-Oda array. This folded dipole, the name itself indicating that a dipole will be folded. Under this folded dipole we have twin lines, V's, biconical, long wire antennas, waverages and rhombic antennas. All this will comes into the dipole category, and from the dipoles also we can make some arrays. That using these arrays we will get more directivity and more gain, and these arrays are curtain arrays and W8JK arrays. These are a subcategory of the arrays. And next we will have another category called as stubs. A stub is nothing but a simple piece of the structure that what we have. Earlier we discussed about that stub in our stub matching. Here also 2 or 3 more pieces will be connected. So that's with different shapes. So this is called as a stub, and under this stub we have conical antenna, that the antenna shape is like a cone. That's why it is called as conical antenna. And the next category is slot antenna. A slot antenna means a small slot will be there. A small slot of the conductor will be there. That slot of conductor will radiate the signal. So under this slot we have patch antennas. Using these patch antennas we can form arrays. Now all this comes under patch antenna. The next category is aperture antennas. Observe the aperture antennas. Under the aperture antennas we have many more antennas like lens antennas. These lens antennas are also called as the dielectric antennas, which will be useful for transmission of very high frequency microwave signals. And then a spiral antennas. A spiral antenna means the structure of the antenna is like a spiral, and it is also called as a helical antennas. Helical spirals will be there, or rectangular spirals will be there. And next, horn antennas. That completely it is a flared out structure. Horn antennas are made up of 4 or more conductors. A flared out structure, a pyramidal horn will be there, a conical horn, biconical horn, different horn structures will be there. And next, reflector structures will be there. That nowadays we are observing these reflector structures widely. For the reception of TV signals we are using a parabolic or a hyperbolic reflectors. The name itself indicating that it reflects the signal towards a particular point. If you are considering a parabola, then at the focus point we will have another antenna which receives the highly focused signal at that particular focus point. That's why this is called as a reflector, a parabolic reflector, corner reflector, flat sheet reflector, and radomes, FSS. All these will comes under aperture antennas. That aperture antennas will be classified purely depend upon the shape only. These are some of the antennas that what we have. Now we will have some antenna terms and parameters which are to be observed and learn to understand or design our antenna. So there are a few important parameters, but even though there are few, just I will give you what are the parameters which exist for any antenna. Now observe, for antenna we are supposed to observe different impedances. That a radiation resistance will be there. I will explain what is radiation resistance later. A loss resistance, a radiation efficiency, all these 3 comes under the impedance parameters of our antenna. and the aperture. Under aperture, the effective aperture, loss aperture, scattering aperture, collecting aperture, physical aperture, and aperture efficiency. All these are related to the physical shape of the antenna. That's why these terms comes under the aperture. And while the noise analysis, we are supposed to consider the antenna temperature. Antenna temperature decides the noise parameters. That's why under noise we are supposed to observe the antenna temperature. And next comes to the regions around the antenna. Around the antenna we have three regions. It's a near field and far field. In the near field we have it was subcategorized as two more: radiation near field and reflective or reactive near field. So two near fields will be there, and so total three fields will be there. Those fields are very very important for observation of our radiation pattern around the antenna. That's why we are supposed to observe this region also. We will discuss about these three later. And what are different types of polarizations which may comes from the antenna, or which will be generated by the antenna. And so already we discussed about this one, that a linearly polarized signal can be generated, a circularly polarized signal, or the elliptically polarized signal can be generated. And the general parameters are what is a steradian, and what is the power density of the antenna, and what is the radiation intensity of the antenna we will discuss. And according to the directional aspects, in the two-dimensional pattern, according to the directional aspects, we are supposed to observe first null beam width or beam width between first nulls. In short, it is also called as FNBW. And half power beam width, this is also shortly called as HPBW. And resolution of the antenna. These three are the parameters what we are supposed to observe, and they will come under the two-dimensional aspects for the directivity or directional aspects. Similarly, the three-dimensional aspects and three-dimensional directional aspects will be there. They are called as the beam area, beam efficiency, isotropic source directivity, and gain. So all these are three-dimensional directional aspects. Like this, we have many more parameters related to the antenna. All these parameters are related to the antennas. They will be useful for understanding and observation of our antenna design. Now we will discuss about a basic antenna, simple antenna, that is called as Hertzian dipole. Hertzian dipole is the basic antenna which was given by Hertz. That this Hertzian dipole is the base for remaining all complex antennas. Whatever it may be the antenna we are supposed to manufacture or analyze, this is the basic antenna. That's why just in brief we will discuss about that Hertzian antenna. What are the parameters of that Hertzian antenna? I'll give. Now observe the Hertzian dipole parameters and characteristics. This is the root of many advanced antennas. So whatever it may be the antenna we are supposed to manufacture or analyze, we are supposed to observe the Hertzian antenna initially, and using this one only, as the remaining all can be manufactured. And it consists of two spread conductors of two wire transmission lines. Just observe here, this is our entire dipole antenna. For this dipole antenna, two conductors will be there. This is one conductor and this is another conductor. Between these two conductors, using a transmission line, a two-wire transmission line, we will feed the signal. So a little gap will be provided between two conductors to feed the signal. So that's why whenever the signal is fed, so one particular conductor will be make one pole, another conductor will be make another pole. That's why it is called as a dipole. This is a simple dipole antenna. That the next point is, each conductor is lambda by 4 in length. So this is lambda by 4 in length, and this is also lambda by 4 in length, and the total it is lambda by 2. Simply a Hertzian dipole is also called as a lambda by 2 dipole. So what is the total span of our lambda by 2 dipole? So a lambda by 4 for one conductor, lambda by 4 for another conductor. Between a small gap will be there, but we will ignore that gap because so we are feeding the signal through that gap. So the total length of the dipole will be taken as just lambda by 2. So it is also called as a lambda by 2 dipole. Now we will observe what is the basic radiation from a dipole. We observe the basic structure of our dipole. Now how the radiation will comes from the dipole, and what is the basic principle. Just you observe the figure that what I am showing. Now let us consider this is a dipole. And so for this dipole, whenever we are applying the signal, the gap is the gap and the signal applied is not shown here. Even though it was not shown, just you need to imagine that it was made a dipole. This is a positive pole and this is a negative pole. And whenever a positive pole and negative pole was made, obviously we know that a field will be generated from the positive pole to the negative pole. That's why they are called as the field lines. That a field line will be generated from the positive pole to the negative pole. This is what we are observing at a time t is equals to 0. So whenever a dipole was observed, immediately a field will be generated from the positive pole to the negative pole. But we are not stopping there. What we are doing is just we are making these poles to move to and fro. That as the time increases, this positive pole a little bit it comes down and this negative pole a little bit goes up. That is, the current is varying here. So when the current is varying, what happens to the field that what we are observing? The field what we are observing will little bit bulges and just it will be shown like this as shown in figure. Even though it bulged, it is still attached to the dipole only. Just observe here that the wavefront moves out as charges goes in. It moves out, but it will not be detached even in this particular case. But what we are doing is we are still increasing the time. As the time increases, for the time increases, at some time what happens is these two charges will be swapped. Whenever these two charges are swapped, obviously the direction of the electric field also changes. Initially the direction of electric field is like this. Here the direction of electric field is like this. But what happens here is the direction of electric field is opposite to the original one. With this conflict, what happens is the previously generated field will be detached from the dipole and moves to the free space. That here the point given is as charges passes the midpoint, the field lines cut and loose. That because of the change in the direction of our electric field, that you can observe that particular phenomena here. Whenever the electric field is changed its direction, the previous one will be detached from that one and goes to the free space. And as the time moves on, this will be bulged, or simply you can imagine the smoke, and as a smoke, this particular field will goes to the free space as an electromagnetic wave. This is called as wavefront. This wavefront will moving out from the dipole. So if you observe, just to get a detachment between this field and our dipole, definitely the charges must be oscillate to and fro. If there is a still position for the charge at the top and bottom, this particular field will exist and attach it to this particular dipole only. If it is to be detached, obviously the charges must be oscillate to and fro. So this is a simple radiation principle. Now when we will get radiation with this simple phenomena, we can observe different conditions and different scenarios. So purely depend upon the motion of the charge, we will get radiation. If the charge is not in motion, if it is stationary, we will not get any radiation. That is the first point, that what we have here, there is no radiation for a stationary charge, that the charge must be moved. How the charge must be moved? The charge must be moved with variable velocity. That's if the velocity is also fixed, that there will be no radiation. So it must be moved with variable velocity, or the conductor that what we are considering must have a special shape. That if the conductor is a straight line, then there will be no clearly radiation will not be there. So if the conductor is simply bent in another shape, some radiation will be there. Or if the charge is moved with different velocity, then also some radiation will be there. That a time varying charge always gives you the radiation, a stationary charge will not give us the radiation. That is a simple principle of radiation here. Now we will observe different fields around the antenna. So what are the fields, or what are the regions around our antenna, and how to analyze them, and what is the use of those regions? Just you imagine. So we are very near to an antenna. Whenever we are very near to an antenna, you can experience some heat. So because of the radiation which is coming from the antenna, you may experience, if it is very near, or you may experience some heat. If you are moving away from the antenna, the effect of that heat will be reduced, right? Similarly, so if you are going to calculate the radiation pattern, this heat may change the radiation pattern. So whenever you are calculating the radiation pattern, you are not supposed to stand very near to the antenna. So this is a general example that what I gave. Now what you have to do is just you have to observe what is the region which is suitable for calculation, or which is suitable for observation of radiation pattern. Now observe here, around the antenna, the regions are classified as reactive near field region, radiating near field, or this is also called as Fresnel region, far field or Fraunhofer region. These are the three regions around our antennas. Among these three regions, the far field region is a very important region, because in the far field region the effect of our antenna parameters are very less, and the noise effects are also very less. So we are supposed to go for a very far from the antenna, that's why it is called as a far field region. So very far from the antenna, and we are supposed to calculate all the parameters of our antenna. But what we do is just we will observe the remaining two also. Now what is far field or the Fraunhofer region? Is the far field is a region very far from the antenna, that's why the name is far field. In this region, the radiation pattern does not change the shape with distance. In the near field region, what happens is, if you are observing the radiation pattern will rapidly vary with the distance. That is directly proportional to 1 by r square, or that is directly proportional to 1 by r cube. But in far field region, the radiation pattern is proportional to 1 by r only. So what happens is, even though you are moving for large distances, that radiation pattern will not change abruptly. Definitely you will get some change, but it will not change abruptly. That's why we are supposed to go for the far field region for calculation of radiation pattern, gain, directivity, etc. And if the maximum linear dimensions of an antenna is d, then for far field region, these three are the conditions which are to be satisfied. That the distance is must greater than 2d square by lambda, where d is the largest dimension of the antenna. If you are considering a parabolic reflector, the diameter is d. If you are considering a linear array, the array length is d. That the distance which is which is more than 2d square by lambda is said to be the far field region. For that, r must be very much greater than d, and r must be very much greater than lambda. If these three conditions are satisfied, then this particular distance is simply said to be far field region or Fraunhofer region, which is most suitable for all calculations. And the next region is reactive near field region. So what is reactive near field region? The name itself indicating that it is a reactive field. So for each and every change, the electric field and magnetic field will be affected. So the temperature will be there. So with a slight variation in the temperature, the electric field and magnetic field will be varied. And for slight variation in the signal, the electric field and magnetic field will be varied. And the field is proportional to 1 by r square, and the field is proportional to 1 by r cube. As the distance is slightly varied, the field will be abruptly varies. Now which region will be considered as this reactive near field? For that, now the boundary of this region is just r less than 0.62 and the square root of d3 by lambda. So the distance which is less than this particular value is always said to be the reactive near field. In that reactive near field, as I said, there will be no calculation we are supposed to consider. And the next field is radiating near field. This is also called as Fresnel region. So this is at this region the radiation will start. Till then there will be no radiation, as we observed in our dipole radiation. There will be no radiation, but the field will be there. It's up to the particular point there will be some field, but after that particular point only the radiation will comes into the picture. Here this particular region will have some radiation, the basic radiation will be there. This basic radiation is not suitable for transmission. So whenever we are going to the far field region, then only it will be useful for the observation of our parameters. So here clearly the region between our reacting near field and far field is called as the radiating near field. So what is the boundary? The boundary is lies between 0.62 square root of d cube by lambda less than or less than 2d square by lambda. That is in between our reacting near field and far field. The field is called as, the entire region is called as radiating near field, or simply it is called as Fresnel region. Now what I do is just I will show you a figure to understand this clearly. Just you observe this figure. So this is an antenna that what we have with the largest dimension d. Now very near to this one is called as the reactive near field, that the distance is up to 0.62 square root of d cube by lambda. This is called as reactive near field. And from the 0.62 to 62 under square root of d cube by lambda to 2d square by lambda, this region is called as radiative near field. In this one the radiation will starts, but that is not completely up to the mark. After later we can observe the complete radiation. That is a very good radiation in the far field region. The region beyond this 2d square by lambda is called as far field region. So like this, the total antenna surroundings can be divided as three regions. That's the reactive near field, radiative near field and far field. Now how the antenna radiation can be observed? So whenever the antenna is generating some radiation, how it will be observed in our free space? To observe that one, what is the parameter we are supposed to consider? The parameter we are supposed to consider, or the sketch for that particular radiation, is called as a radiation pattern. That how the pattern will be. Just you imagine a simple scenario. we are considering a mobile tower. So for that mobile tower, definitely some antenna will be there. So that mobile tower must radiate or must receive the signal, so wherever the mobile is in and around that one, that it has to generate a radiation or it has to receive the radiation 360 degrees around that one. That whenever the radiation is coming from the antenna or whenever the radiation is to be received by the antenna, that it must cover all the 360 degrees which are near to the antenna. So if you draw that particular radiation, then that is said to be the radiation pattern. So what is that radiation pattern? How to draw that one? Here two types of patterns are there, that is power pattern and field pattern. Just you observe. The radiation pattern defines the variation of the power radiated by any antenna as a function of the direction away from the antenna. As I said, this will be taken in far field region only, as the near field is not suitable for taking any one, that we will go to the far field region. In that far field region, what we do is we will observe the radiation pattern, that the power or the field, we will calculate the power, then that is said to be the power pattern. If you calculate the electric field, then it is said to be the field pattern. Whatever it may be, that radiation pattern is simply a function of direction. That what we do is we will consider the angle, and in which angle we have, that's around that one, and at that particular angle what will be the power or what will be the field we will observe, then it is said to be the radiation pattern. Now observe the sketches of radiation pattern. So this is a typical field pattern of an antenna, that this is a three-dimensional sketch, that exactly at this point we may have the antenna, that this is the point where the antenna is placed, and this is drawn for a directional antenna, and in this direction you have maximum radiation, that you can imagine a balloon, that in this direction the maximum radiation will be there, that this particular region or this particular shape is called as main lobe or the major lobe, that the major lobe is along z axis, that as per our example it is considered along z axis, that the radiation is generating along z axis, that's why the maximum radiation will be concentrated along the z axis. So simply remember the word, this is called as major lobe or main lobe, and the remaining all lobes are called as minor lobes, that this radiation is not required for us, but it is existing. This is called as a minor lobe, this is a minor lobe, this is a minor lobe, this is a minor lobe, and this is also called as minor lobe. But among these minor lobes, exactly the lobes which are existing back to the antenna, they are said to be the back lobes. The word clearly back describes the lobes which are existing behind the antenna, then they are said to be the back lobes, and they are called as minor lobes or side lobes. Clearly three types of lobes will be there for any radiation pattern. This is called as the major lobe, a radiation pattern, you can imagine that one as a balloon, and this is called as side lobe or minor lobe, and they are called as the back lobes. Now it's whenever there is no radiation, that this region, just you observe this region, there is no radiation in this region, observe this region, there is no radiation, right? Just observe this region, there is no radiation. Like that, the region where there is no radiation, they are called as nulls. Simply null means zero radiation will be there. Now this field is a function of theta and phi, where theta is called as the elevation angle, phi is called as the azimuthal angle. With the help of theta and phi, what we do is, by varying this theta, by varying this phi, we will observe what is the power strength or what is the field strength at that particular angle. That's we will draw that one. So that's why this field is a function of theta and phi, right? So all the field components of electric field will be drawn with respect to theta and phi on a graph sheet. Then simply what you will get is a radiation pattern. If you cut this one, then you will get a two-dimensional radiation pattern. That two-dimensional radiation pattern for the power as well as field will looks like this. Just you observe. This is a three-dimensional plot that what we have, that what we observed earlier, and if you cut this one, a cross-sectional view of this one is like looks like this. This is called as a polar plot. Then this is also called as the major lobe. Here also you can observe the maximum field strength. So in this particular direction, this is called as major lobe, and all they are called as the minor lobes, and this particular one is called as back lobes. So this is a three-dimensional structure, and the cross-sectional view of this one will gives you like this. This is a two-dimensional structure or polar plot. And if you are drawing this particular radiation pattern on a decibel sheet, that's on the y-axis what we are taking is the decibels, the power or the field in decibels. On x-axis what we are taking is a angle. that it's a completely elevation angle or azimuthal angle. That's as per the requirement. You can take either theta or phi. Here what we took is theta. So if we are calculating the power with respect to theta and draw, then this is the pattern that what we have, and this major one as are the maximum one is said to be the major lobe, and the adjacent one, this one and this one are the same. So this is the first side lobe, this is the second side lobe, and this is the third side lobe. Like this different side lobes, and this may be the back lobe, exactly 180 degrees opposite to the main axis. This is said to be the back lobe. And the regions where we have zero radiation, this region, this region, this region, this region, this region, all these regions are called as nulls. Just all these are different patterns of radiation, nothing more than that. Just once again observe, this is the major radiation pattern that what we have. This is the typical field pattern of an antenna, and the cross sectional view of this one will be like this. And if you are drawing that one on decibel sheet, that it looks like this. So whatever it may be, that you can consider that one as the radiation pattern either for power or field. Now for any calculation purpose, so what we require is the normalized radiation pattern. So what do you mean by normalized radiation pattern? You may have the maximum value for the radiation pattern, maximum power or the maximum field for that particular radiation. Just you divide all the values with that maximum and redraw the structure, then it is said to be the normalized radiation pattern. So for that normalized radiation pattern, the maximum value is 1. This is only for mathematical purpose, right? Just you observe that normalized radiation pattern. With the help of that normalized radiation pattern, we can have a few more parameters like FNBW and HPBW. Just you observe the structure. This is a normalized radiation pattern. As I said, all the values will be normalized, that all the values will be divided with its maximum value. So the maximum divides with maximum value always gives you the 1. Similarly, all the values will be divided with its maximum value, will have the respective values. Now this is a major lobe, and all these are the side lobes that what we have. This is first null, that what I define is, or that what I say is, this is the first null. First null means the null which is adjacent to the major lobe. This is also the first null, the null which is adjacent to the major lobe. Now clearly remember, I will define two important parameters. They are called as half power beam width and beam width between first nulls. That's also called as first null beam width. Now come to the half power beam width. What is half power beam width? That the beam width, BW stands for beam width. It is not bandwidth, don't get confused. It is beam width. The width of the beam exactly at the power is half. So if the maximum power is 1, actually this is for field, that if you consider this one for power, then the maximum power is 1, and the half power line you are supposed to draw here. Somewhere the half power line will come into the picture, and if you take the angle between these two half power points, then that angle is called as half power beam width. But here this pattern was drawn for field, not for power. That's why it was taken as 0.707 of the maximum. As you have a relation between the power and field, P is directly proportional to E square. So with that simple relation, if the field is maximum, then 0.707 of it will be considered as half power beam width. So this is one of the important parameters which describes the directivity of the antenna and resolution of the antenna. So if you want more directivity, this must be very less, and if you want more resolution, this must be very less. Clearly remember that point. For more resolution and more directivity, the half power beam width must be very less. And similarly, you have one more parameter that is called as FNBW, beam width between first nulls. Consider this first null. The angle between these two nulls is said to be the beam width between first nulls. So these two are the two important parameters which describes the directivity as well as resolution we are supposed to calculate. And so as per one theory, it's a half power beam width is half of the first null beam width approximately. So for the calculation of half power beam width, take the FNBW and make it half, or for the calculation of FNBW, take the half power beam width and make it twice. So simply from this normalized power pattern, we can obtain these two parameters that they were explained here. That the FNBW is nothing but the beam width between first nulls, that is the angle between two nulls that are observed adjacent to our major lobe, they are called as the first nulls. And half power beam width is nothing but the angle between the two half power points for cross sectional view of our power pattern. So these are two important parameters we are supposed to observe. Now we will observe few more parameters of our antenna. So just I will give you the definition of all those parameters and the significance of all those parameters. Observe now. The next parameter is beam area. The name itself indicating that it is some area, but it is not area, it is a solid angle. Solid angle is nothing but a three-dimensional angle. So the beam area or beam solid angle of the antenna is given by the integral of normalized power pattern. What we have to do is just we have to take the normalized power pattern and integrate it over theta and phi, azimuthal angle and or elevation angle. Then you will get the total solid angle through which the radiation comes into the picture. Then that particular area, the total solid angle is said to be the beam area, and this is a simple equation which describes that beam area. And the next parameter is directivity. Whenever we are designing an antenna, clearly remember they will describe how much directivity they want. So for the designing of an antenna, they will decide, so this much directivity I require, this much gain I require, at this particular frequency I am supposed to operate the antenna. So this directivity is one of the important parameters which is supposed to be observed for any antenna, which always gives the directional aspects of the antenna radiation. So in which direction the radiation is maximum, so in which direction we are getting zero radiation, in which direction we are getting a very small radiation, that the maximum radiation will be in which direction can be obtained using our directivity parameter. Clearly remember, this directivity will not describe the efficiency of the antenna, just it describes in which direction it gives the maximum radiation. That's why the directivity is a fundamental antenna parameter. It is a measure of how directional the antenna is or the antenna radiation pattern is. If the antenna is radiating in all directions uniformly, then what you can say, it is simply it is zero directivity. That is, in no direction it is generating the radiation pattern, in all directions uniformly it is generating the radiation pattern, so it is zero directional antenna, or it's the directivity is simply said to be 1. So how it is defined? It is defined as the ratio of maximum radiation intensity to the average radiation intensity of that particular antenna. So simply directivity is given as maximum radiation intensity divided by average radiation intensity. So this is one of the important parameters we are supposed to remember. And the next parameter is gain. So as I said, the directivity is related to the directional aspects of our radiation pattern. Now the gain is related to the efficiency of our antenna. So how much efficiently it is generating the radiation pattern in a required direction, that can be obtained or observed using our gain. So this gain and directivity are very closely related, but they are not same. Directivity is related to the directional aspects and the gain is related to the efficiency aspect, and we have a relation between them, that gain is equals to efficiency of the antenna into directivity. That what is given here. The term antenna gain describes how much power is transmitted in the direction of peak radiation. So how efficiently, how much power is efficiently transmitted in that particular direction can be described using our antenna gain. So as I said, gain is equals to efficiency of the antenna into directivity. This is one of the important parameters. Always this will be described at the time of designing of our antenna. The next parameter is aperture. Aperture is nothing but cross-sectional view. Just you observe different apertures are there for different antennas. Here the physical aperture and effective aperture, these two will comes into the picture while designing the antenna. Physical aperture means just a physical cross-sectional area of the antenna whenever we are observing the antenna. So what is the physical cross-sectional area? Simply it is said to be physical aperture. Then what is the effective aperture? Among those physical aperture, the effective area which is used to radiate or receive the electromagnetic wave, then it is said to be the effective aperture. We may not get the entire radiation from the entire physical cross-sectional view, but so some of the area may be blocked or some of the area may be inefficient to radiate the electromagnetic wave. That particular area will be removed and the remaining area is called as the effective aperture. Or similarly, only few part of the area will be useful for reception of this signal, then it is called as the effective aperture of that particular antenna. So how the effective aperture is related with the gain? Just you observe, the effective aperture of the antenna is equals to lambda square divided by 4 pi into gain of the antenna. So this is the relation between effective aperture and gain. So the effective aperture or the effective area can be measured on actual antennas by comparing with that one with a known antenna. So with a known antenna, how much effectively how much area will be useful for transmission of the signal for a known antenna, and for a designing antenna how much area will be useful for transmission of a signal. So these two will be compared, and after comparison they will calculate the effective aperture of our antenna. And the next parameter is radiation resistance. So what is radiation resistance? The radiation resistance is a hypothetical resistance, it is an imaginary resistance which delivers the power same as the power which is delivered by the antenna. So whenever we are supposed to replace our antenna with any resistance in a circuitry, we are supposed to consider this radiation resistance. So the amount of power which is delivered by the antenna and the amount of power which is delivered by the radiation resistance, both are same. Here we have the radiation resistance for different antennas. The basic definition of radiation resistance, or the equation for radiation resistance, is the power radiated by I RMS square. So after simplification of this one for different antennas, like lambda by 2 dipole, we will get approximately 73 ohms, and for a lambda by 2 monopole, half of this one approximately 36.5 ohms, and for a lambda by 2 folded dipole, 4 times of this one, that is approximately 292 ohms. So simply remember that the radiation resistance is nothing but a resistance, a hypothetical resistance which can be used to replace our antenna and which will deliver the power same as our antenna. The next parameter is return loss. So what is return loss? The name itself indicating the power which was lost when the signal is returned. What we do is we will consider an antenna and we will apply the signal. So our main requirement is to total radiation from the antenna. So without any reflection, so we require all the signal must be radiated to the free space through antenna. But what happens is under some circumstances the signal will be reflected or the returned from our antenna. So whenever it is returned, how much amount of power was returned is can be calculated using our return loss. So this return loss is related to the standing wave ratio. Standing wave ratio is related to the reflection coefficient. So whenever there is a reflection, this return loss will comes into the picture for an antenna, and simply it is given as return loss in decibels is equals to 20 log 10 standing wave ratio divided by standing wave ratio minus 1. It describes how much amount of power was lost when signal is applied to the antenna. Now observe the dual characteristics of our antenna. So why we are saying that them as dual characteristics? That the antenna is an interface between the circuitry and free space. So whenever we have a circuitry, that voltage and current will comes into the picture, and whenever we have a free space, that electromagnetic field will comes into the picture, E and H will comes into the picture. So clearly this antenna is an interface, that's why it will show so both characteristics. That the dual characteristics of the antenna can be simply observed using this simple figure. Observe this figure. Let us take this is the antenna that what we have. For this antenna structure, at the input end all the circuit quantities will be there. The circuit quantities are like nothing but antenna impedance, the radiation resistance, all these are the physical quantities, the antenna temperature, and these are called as the circuit quantities. Along with them the voltage and current also will come into the picture at the input of our antenna. And what are the physical quantities of our antenna? What is the size of the antenna? What is the weight of the antenna? And what is the current distribution of the antenna? This is simply the antenna transition region. Now after this one what you will get is completely radiation. So in this radiation, the space, the radiation in the space, different parameters will comes into the picture. The field patterns or the power pattern will be there. So in the field pattern we are supposed to observe the electric field in theta direction, electric field in phi direction, and the phase difference between all these fields. And what are different polarizations we have, like linearly polarized signal, circularly polarized signal, elliptically polarized signal, and a power pattern can be observed in the space. The beam area can be observed, the directivity can be observed, the gain can be calculated, the effective aperture can be observed, and the radar cross section also can be observed. That is, all these are for the space of our space quantities. So here clearly the antenna will be acting as an interface between the circuit quantities and space quantities, and these quantities will be converted to this with the help of an antenna. That's why the antenna is always possesses dual characteristics in our general scenario. Now we will derive one important equation called as Friis transmission equation. This Friis transmission equation is useful for calculation of power received, calculation of power transmitted, or gain, or if there is unknown gain of the antenna, that also can be calculated. And for different measurements, this Friis transmission is useful, and this is a very important and easy equation. Just to observe how the Friis transmission is derived. For the Friis transmission equation, let us consider a communication system which consists of a transmitting antenna and a receiving antenna. The distance between these two antennas is r. The transmitting antenna has a gain of gt. Let us take the gain of transmitting antenna g suffix t, gain of the receiving antenna gr, and the effective aperture of the receiving antenna is aer. Now let us assume that the power pt, that is the power in watts, the total power is delivered to the transmitting antenna. Whenever this power is delivered to the transmitting antenna, if we are going to calculate the power density is nothing but the power per area. So the power density is equals to the power transmitted by the area of the radiation. What is the area of the radiation? Here we are assuming that the radiation is like a sphere. So the area of the sphere, the surface area of the sphere is 4 pi r square. So the power density at a distance r. So here where we are calculating, if the transmitting antenna is transmitting the power at distance r, we are calculating the power density. So the power density is equals to power transmitted divided by the cross sectional or the simply surface area of our radiation pattern, 4 pi r square. So this particular power density is observed at the receiver, right? Now if this is to be received by the receiver, then it is multiplied with aer. So prior to that one, this power density will be multiplied with the gain of the transmitting antenna. Yes, we have some gain to the transmitting antenna. This transmitting antenna will have some gain, right? So the power density will be multiplied with the gain of the transmitting antenna. So the modified equation is power density is equals to pt by 4 pi r square. This is the original power density, now multiplied with the gain. Now this is to be received by the receiving antenna, right? But the receiving antenna will have some effective aperture. Let us take the effective aperture of our receiving antenna is aer. So aer is the effective aperture of our receiving antenna. So the total power receiver is equals to this power density multiplied with the effective aperture, that is pt by 4 pi r square gt into aer. And earlier we observed that effective aperture has some relation with the gain, that ae is equals to lambda by 4 pi into gain. This is the relation between effective aperture and gain. Now this gain is nothing but the gain of the receiving antenna. aer is equals to lambda square by 4 pi into gr. Substitute here, then what we will get is PR is equals to PT GT GR lambda square by 4 pi r square. This particular equation is an important equation. This is called as Friis transmission equation or Friis transmission formula. So if you remember this particular equation, then you can calculate the received power by the receiver or the transmitted power if the remaining terms are known to us, or you can calculate the unknown gain if you have two similar antennas. So like that, this equation is very much useful for calculation of many parameters. That's why you are supposed to remember the final equation PR is equals to PT GT GR lambda square by 4 pi r whole square. This is a Friis transmission equation.